Good afternoon, everyone. Good morning to some of you as well. Welcome to the Phius Passive House Institute US webinar on Phius versus PHI Part II. Let's talk about summer comfort. Today's presenter is Katrine Klingenberg. She's the Executive Director and Founder of Phius. Today's webinar will be approximately 1 hour. That includes some time at the end for some Q&A. If you have any questions during the webinar, please use the question box. You'll see it on the right-hand side of your screen, and we'll try our best to answer all your questions at the end of the webinar. If we don't get to them, we'll try to answer them after. And once again, we have Katrine here. I'm going to hand it over to Katrine and enjoy the webinar.
Thank you, Anissa. Hello and welcome everyone to our second installment here of talking about the lessons learned on our journey of passive building standards implemented in North America. This session will be on cooling and summer comfort, and the reason we put that on I'm going to move my control panel here for a second. The reason we decided to talk about this particular topic is obviously it is summer, and for us at Phius, things slowed down a little bit more, at least in terms of travel, and we get to go more often than normal down to Champaign-Urbana from Chicago to spend some time in the Smith House, and a few of you might know that was the very first passive house that was designed to meet the PHI targets in 2002, and it was completed in 2003. Our starting photo here, this is the Beach Green Dunes project, multifamily, so really this is not the most recent, but one of the most impressive, largest affordable projects that we have gotten to in this 15-year journey from this very first single-family home in Urbana to now multifamily projects that are being constructed across the country. And it's time to reflect a bit on the lessons learned and where we're coming from, where we've been, where we are going, and also what is still on the menu, essentially for research. What do we still have to figure out? How well are we doing in our journey to high quality, low carbon, super comfortable and resilient projects? So quickly here again, the link, I believe Anissa had posted that one as well from part one. Part one, we talked quite a bit about the different criteria, a difference in heating demand criteria and cooling demand criteria. This particular segment will talk and zoom in a little bit more on the difference between the peak loads between the two different standards. The webinar is approved for continued education credits. You can see the self-reporting code at the end of this presentation. All right, so I started the last webinar as well with this slide, and again, there's an acute urgency to me personally. My main motivation behind popularizing passive building standards in the United States, and really with a view towards global adoption, is the concern about climate. And as you can see right here, the temperature that exceeds 100 degrees F will exceed the number of days. I'm sorry, this graph shows the number of days which the temperature exceeds 100 degrees by the late 21st century, and these three different depictions of the United States obviously show different scenarios. In the middle, the low emission scenario that people have been trying to come to consensus on, and the higher emission scenario. And as it looks like, we have fallen a little bit asleep at the wheel, and it is becoming more and more likely because we're late in the game, and the global community has not been able to come to consensus in terms of global carbon reduction action. We might be looking at this point at the higher emission scenario. That means the climate is warming, and the cooling condition and the summer comfort condition is becoming more and more an issue, and we need to get that right because it will be part of our adaptability, our resilience, and our future comfort in the buildings that we are building today. So just very quickly, a few articles that were recently published that again reminded me of this urgency, a little bit frustrating, maybe depressing. New York Times magazine was devoted in its entirety 2 weeks ago to an article that was titled "Losing Earth," and it was chronicling the decade that we almost stopped climate change. And my first awareness happened of the issue happened during the Earth Summit in 1992. So I really missed that whole history that happened before, where people were already very well aware of climate change and where they started to argue for very urgently needed unified action globally. And also recently in the USA Today, there was another article that basically confirmed what is written up in this magazine, that we knew everything we knew already in the 70s and 80s about climate change. There has been no breakthrough significant other than that the models have become better and that the predictions now look like they were somewhat underestimating. So all that, just here are the links if you're interested in looking up on that, to make my point that the challenge that we're up against is the hill is getting steeper. And as you likely all know, here quickly a slide from Nixon way back when, the oil embargo. This is our history of the passive building standards and house standards started to take action as part of this initial movement to tackle the problem. Before I move on and recap quickly here the history and then recap quickly what we talked about during last seminar, I want to mention and re-emphasize that cooling, after we, I feel, together have tackled the heating problem quite successfully, Passive House Institute in Germany as well as Phius. We know that situation very well. We have the comfort under control, the principles under control. Cooling from a climate perspective is really becoming very quickly the leading challenge, as we so far don't really have a good way to cool buildings, and currently we're still looking at cooling with refrigerants that have additional challenges to the climate inherent in them. But really quickly here, recapping the history that might explain why we all together as a passive building community and high performance community have a really good handle on the comfort situation in winter, and why we are now up against the comfort condition in the summer. Our common history goes back to the 1970s, Small Homes Council in Urbana, Illinois, first experimental projects, locale, and the researchers from that Building Research Council, then moving on to Canada, much colder climate, perfecting that cold climate challenge in the Saskatchewan house here in Saskatchewan. And then in 1996, after interest in all these high-performance technologies waned in the United States, Passive House Institute in Germany picks up on it, popularizes it for the moderately heating-dominated climate. Yet again, a climate where we don't inherently have a cooling issue, and codifies a standard to which buildings should be built with a focus on an EUI reduction that matches our climate challenge in terms of reduction of emissions related to the operation of buildings. And then from 1996 on to 2019, where we are now, increased interest grows from all over the world in these initial successes of setting high performance standards. And with that, we are also expanding that knowledge into more diverse and more complex climates. And with that, the learning starts. PHI and Phius have this in common, this very solid foundation in cold climate high performance design, but we diverged in 2011 over differences in opinion of what should happen and what would be good design guidance for climates that are a bit more complex and humid in nature, and so we don't any longer have this very clear design scenario where we're designing for a clearly heating dominated climate, or even a clearly cooling dominated climate. That would be somewhat easy as well, but we're now dealing with climates that are not as crystal clear, not as black and white, mixed in between. We're ending up with a spectrum rather than with a very clear guideline. And that's what the Phius Plus 2015 development was all about. We're differentiating our design guidance and strategies to get at this problem. Like, so how do we get a super low EOI that meets our global carbon reduction targets, but also assures thermal comfort in winter as well as in summer? And so this presentation will go through that particular part of the learning of how we tackle summer comfort and not just winter comfort. So last webinar we tackled and looked mostly at the annual heating demands and cooling demands, and I hope we were able to explain that once you move into climates where you have heating as well as cooling and not just a clear heating situation, that since we can't take a jacket off of the building and put on a light jacket in the summer and a heavy jacket in the winter, we need to design for both conditions, and we need to strike a balance between both. And this is why these heating demands and cooling demands are very important indicators for the designer to find that right balance between both conditions. Now, the peak load, I'm going to get to this in a second. I like to expand on that heating dominated clear picture that we have. I feel very solid that about this building science. It has been long-standing, long tradition. Again, here are the 5 principles that the PHI publishes on their website, and is all mainly focusing on the thermal considerations, and it comes from the background of a heating climate base. So we see our common 5 principles here: continuous insulation, no thermal bridging, we have airtight construction, we have ventilation strategies with heat recovery, we have very good windows, and we also, that's it. I went around the other direction here. So a very solid basis in a heating dominated climate, and these things are well known. They work very well. We got them down. And from very early on, work in Europe, this is here from the Phius book that was published in Austria quite some time ago, early 2000s. The mantra for passive buildings was minimize losses and maximize gains. So when we first started our classes here in the United States, that's what we started with. We started with that kind of cold climate mantra. And obviously, as soon as you get into more mixed climates and warmer climates, you're like, will that hold true? So I started telling you a little bit about the impetus for this webinar, and having more time to go down to enjoy the Smith House in Champaign-Urbana. And this is an image right here, early 2003, when they finished the high density blown-in insulation in the Smith House. And it's a fabulous blanket and super warm. And every time we go in the winter, we absolutely enjoy it. It's a slam dunk. The house performs fantastic. So it is a really, really good idea. Air tightness, reduction of air movement, insulation, thermal bridge reduction, all that works great. And here in like this kind of scale analogy, you can see essentially the core principle of a passive building. We're insulating to a point where the internal gains and solar gains, the classic passive strategies, where they almost come into an equilibrium. And only a very tiny additional heating system would be required to make up for that difference. And it is so tiny that basically a 100-watt light bulb could heat a 100 square foot room. It's very, very small. But as soon as we get into climates, of course, where the temperatures are more extreme, we will need more heating. That speaks to the peak loads. And to maintain that comfort in the winter, we need to know what that peak load is going to be. And so in either case, we very likely will not be able to create this perfect equilibrium, and we need active heating to maintain our comfort set point of 68. And we'll look at this in a second, where the 68 set point comes from. So the Passive House Institute very early on was very good in communicating this idea, and they really did an excellent job. They always had these thermal images of coffee pots that were insulated versus the uninsulated coffee pot, and it is a very striking image to the uninitiated, to the non-building scientists, and it's obvious. So the insulated shell keeps coffee hot, and the insulated shell also keeps ice cold lemonade cold. We know that from experience. Now the problem is when you apply that image to buildings in the heating condition. That's fine, because really people are more like hot coffee than like ice cold lemonade. If we get to the cooling condition, things get a little bit more out of whack. So you can see that all of this stuff all of a sudden is on one side. So what initially kind of like got us quite a bit far down the road to heat our building, solar gain, internal gains that we have in the building, is now all stacked up against us. So we really need active cooling, period, because we are not ice cold lemonade. We are human, and we have warm liquid in ourselves. We are putting heat into a super insulated building. So not too long ago, I did a presentation at the MIT Energy Initiative, and there was a question at the end of this presentation, and somebody was saying to me like, "Oh, what are you talking about? Overheating issues? The insulation works just as well for heating as it does for cooling." And well, that's what people say, because they look at the condition of just a cup with hot water in it and a cup with cold water in it. But as soon as you have actually people do things in it, and you add additional heat sources in the building, we realize that at that point we actually do need active cooling. So we're confusing passive insulation and retaining thermal hot or cold thermal energy, but we're confusing things here. With, of course, we can balance this with an active system, but the question now becomes, how good is the passive design so that the active system does not get unnecessarily big? We're still passive designers. Our goal is to design as precisely and as possible away from active heating systems, which are again associated with emissions and increasing global warming. So my image that I offered this student in the audience to explain to him the difference was, so imagine yourself in Times Square with a climate zone 6 North Face puffy coat, and you have the zipper zipped up, no air movement, no nothing, and you're standing there on July 31st, humidity is high, and it's about 100 degrees. Well, not difficult to imagine, it's pretty uncomfortable. And then the student said like, yeah, but it works if I have a cooling system. And I was like, do you want to carry around a cooling system with you in summer? Wouldn't you rather take that jacket off, right? So, and that leads us to the next problem, and that is like, if we are in a climate where in winter we need a 006 North Face climate zone 6 puffy coat, and in the summer we only need a, I don't know, maybe a light puffy coat, we need to strike a balance between the two. Otherwise we are going to have issues. And so is super insulation still a good idea in a mixed climate? And that's exactly the question we have here. So let's look at the peak loads. And the peak loads will very quickly tell us something about the comfort conditions and what we need to design to in terms of active systems to maintain our comfort, and that's what we're going to take a look at here. So as a reminder, we discussed this already a little bit last time, but differences between Phius Plus 2015 and PHI and where we diverged. For peak loads, same situation. PHI promotes a one-size-fits-all, very, very low peak load, 1 watt per square foot, here the 3.17 BTUs per square foot an hour. And the same peak load is suggested for cooling. And for Phius Plus, these peak loads vary by climate. Now, how does thermal comfort, how do we define thermal comfort? And if you look at different people, this is a way here how the PHI Standard 55 has developed a method or to measure thermal comfort when we ask people about that condition of mind that makes us feel satisfied with our thermal environment. And yes, it is a subjective evaluation, but it also shows right here, you see there's quite a range there. It shows a built-in human range of metabolism, for example. Like my partner, Mike Cornages, he has a very high metabolism and feels hot very quickly, very soon. And I'm the opposite. I'm exactly on the other end of the comfort zone spectrum. I get very cold very soon. And if you find yourself in a passive home that is very well insulated and that has no air movement in it, no drafts, a very, very tightly designed comfort zone in the summer, just by metabolism differences, you will find yourself, two people can find themselves on the opposite end of that comfort condition in that building. So it is really important that we understand what the factors are that impact comfort in the summer. And if we're designing for the winter case, air temperature, relative humidity, airspeed, and radiant conditions, we got that under control. I have this next slide right here for you. So when we first started doing training, that was our slide that explained the thermal comfort in winter. And for the winter case, you can see very thick insulation. We have no drafts, airtight construction, super insulated triple glazed windows with a very specific delta there of delta T difference between interior temperature and surface temperature of the glass to make sure that there's no cold draft developing. Very, very minimal air velocity, low flow ventilation. We have a relative humidity range from 40 to 60 because we're humans. We want like some humidity. We don't want it to dry. And we have our air temperature set point set to 68. So in the winter, that works perfectly fine. Relative humidity, as long as we can keep it in that range, typically it's not a problem to get there if we have an ERV. If we don't have enough relative humidity because it's cold outside and very dry, we might just put a pot out of water out, or we have a humidifier. We got that very well worked out. That leads to nice comfort. The temperatures, because of the insulation of the exterior surface temperatures, are raised. Radiant conditions are great. So winter case works like a champ. In our early training slide decks, then we followed up with the summer case. You can notice right here that the insulation from this slide to this slide, insulation shrunk. So very quickly, it is obvious, back to my example of the thick North Face puffy coat for climate zone 6 wearing on Times Square in summer. You don't want that. You want a lighter coat if you're a building and you can't take it off. You want the right in-between balance that works for the winter case and the summer case. So when we talked about last time about the heating demand and cooling demand, that will give you an indication of where that balance is. Now, the comfort condition inside of the building for the cooling, now we get quite a bit more challenges, because so air temperature 77, we inherited that set point from the PHI, and at this point, this presentation, actually I'm suggesting that we should reevaluate that, because measured data from completed projects shows that that is kind of cutting it close. especially when we are going to look at humidity here in a second. Air velocity. So cold climate design guidelines make it airtight, no drafts because drafts are uncomfortable. Well, guess what? In a summer comfort condition, no drafts are a challenge because now the temperature is warmer and our own body has a cooling capacity, sweating, evaporation. There's no draft. That evaporation is inhibited and it is very uncomfortable. So not saying that airtight construction is not a good idea, but I'm saying that there might be some additional elements needed to make sure that we actually can evaporate if we design for such a kind of tight comfort zone in the summer, i.e. fans. Or higher velocities of the ventilation system that delivers cooling. In my home, for example, I have one of these new CERV systems, and they have a recirc mode for cooling, and that recirc mode runs at a higher velocity, and it actually feels very comfortable. Coolish air is coming out of the diffusers, and it's coming out at a higher air speed, which assists evaporation. So, and then last but not least, the radiant conditions. Well, in the summer, the temperatures are still warm. So they are not cool. They are not taking heat necessarily away from our body. Then this delta right here that we have for the window condition, does that hold true for windows? Turns out that that delta actually stems from cold air pooling in front of a full height window in the winter condition. So the answer is no. We have to reevaluate those radiant conditions and their effects on the body and reassess. So under Phius Plus and our switch to the WFI passive tool, we actually adjusted for these gaps in understanding comfort and in understanding the cooling case. So you can see right here the principles wheel that Fraunhofer and Phius have come up with going forward actually includes the classic cold climate design parameters: insulation, thermal bridge elimination, air tightness, heat recovery ventilation, and the radiation control and high quality glazing. But it also adds, on the thermal side of things, shading and daylighting as a very important feature. And then under this red line that I drew right here, actually hygrothermal impacts on comfort and the energy balance. So let me repeat this again. Those 5 initial principles that we started out with, dating back to the 70s, early passive house pioneers in North America, we got them very well worked out. Cold climate works like a champ. But in moving into more humid and more mixed climates, we realized that we were missing some critical aspects, and now we're adding moisture and the relationship between moisture and temperature to the whole picture. And with that, the conclusion here is that static simplified whole building energy balancing to design and verify projects is still a valid tool initially, but it needs to be supplemented by dynamic hourly modeling to assess moisture and comfort accurately. So, and that's what we did by basically building that simplified tool on top of WFI Plus, which with a very easy click can switch to a dynamic mode to assess those very, very critical things for summer comfort. So let's look at hygrothermal and look at the definition of hygrothermal. So what exactly are we talking about here? We're looking at the relationship between temperature and humidity. It is not just the thermal effects on the envelope that we're looking at now. We're looking at the moisture in relationship to humidity and how that moves in and out of the building. The cold climate passive house case, you'll say like, oh, we've been looking at this. Yeah, from a perspective of durability, we have been looking at this for from the beginning. Even the pioneers knew, like, if there's moisture that moves into the wall assembly, we'll get condensation and we get deterioration. Now, that's for the winter case. But in the summer case, there's an added component to this, which makes the summer case so much more complex. So the hygrothermal relationship between temperature and humidity is the critical factor to understand if you assess comfort in a passive building that is now so tightly designed for a very narrow comfort zone that we're aiming for, that we can then service with a very well-sized, not oversized mechanical system where we're trying to really zoom in and be very precise with our design. So the hygrothermal microclimate, the relationship between temperature and humidity, is an essential part of indoor environmental quality, and we need to understand those heat and humidity flows to be able to assess what the systems should look like, our active systems that we still need to maintain comfort. And that heat and moisture flow is very much defined by the climatic conditions that are present in that particular location. So again, it will not be an as simple recipe as we have for the cold climate situation. We will have multiple different complex combinations of these factors that we have to assess for comfort in different climate combinations. So Dr. Hartwig Kunzel was presenting on this topic at the 10th annual Passive House Conference in Chicago already, and he made very clear, if you're in a heating climate and the comfort range that you're trying to design for is typically outside of your kind of temperature swings. So it is in the warm zone, and your temperature swings happen in temperatures mainly below that comfort range. At that point, simplified method is totally appropriate. No dynamic modeling really is required for assessing comfort, because we understand those principles well. As soon as you go into a cooling and mixed climate, and your temperature amplitudes are zigzagging around your comfort zone, you have diurnal swings from hot to cold, and your comfort zone is right there in the middle, the situation of comfort becomes quite a bit more complex and needs hourly assessments to properly design for it. So once we look at our energy balance, and we get our outputs here from WOFI for the winter energy balance as well as for the summer energy balance. So the winter energy balance, pretty clear. We minimize our losses, we maximize our gains. In the summer, we really need to optimize our gains and optimize our losses depending on climate. So are we in a climate that is 50-50 heating and cooling? Are we in a climate that is very humid, that has a lot of latent energy that adds to cooling and comfort issues? Do we have natural ventilation available to ourselves even for a passive cooling strategy? Are we in a city where the outdoor air is polluted, not just latent, that prevents us from opening a window? So we're starting to have a much more complex situation that we need to analyze and then come up with appropriate responses. And here are a couple of the climate factors that go into assessing the comfort conditions for the summer case. It is the heating degree days, cooling degree days, the design temperature for winter as well as for summer, humidity, solar radiation, night sky radiation, ground temperature. And this is still not all of it, but this is the bulk, the most important ones. And I'm showing here the ICC climate map again of the United States, just to point out that there's this black line in the middle there that kind of divides 2/3 to the east from like the west, and that is the region that has significant humidity issues, and we'll see here in a second what that does. So the kind of like, you can see that this climate zone map is kind of like a layer cake. It's more or less parallel horizontal lines and organization. The ASHRAE world map looks similar, kind of like in North America. There we have kind of like a horizontal layer cake organization. But once you look at the different factors in more detail, you can see that there are some, such as like humidity, that start to organize themselves more in a vertical pattern, and this is where it gets a little bit more complex. So from there, I showed this image last time. So if you combine those two, the horizontal layering of the heating demand and cooling demand, with the peak loads, you can get quite some different peak load conditions, even though you are potentially in the same layer cake zone in terms of heating demand and cooling demand. So this is a very important criterion and indicator for the designer to know your peak loads, because they can be different from the pattern of the heating demand and cooling demand. So that's that. Then this slide here speaks to these spectrum patterns that we now see develop. We need guidance for annual demand and cooling demand that is now going from 1 to 12 for heating and from 18 to 1 for cooling. So that makes sense. That's intuitively understandable from high to low. But interestingly enough, for the peak loads, if you look at that, for the peak heating load, it makes perfect sense. Yes, in the hot climate, almost no heating. It goes down to 0.8. But for the peak cooling load, even in the very cold climate, we still have a peak cooling load of 2.5. And that speaks to what I was mentioning earlier. We're more like hot coffee than cold lemonade. All the internal gains, people, solar gains, that adds to the balance, to the energy balance that has to be cooled out of the building. We have we don't get a bonus from heating the building with ourselves and solar gains like in the winter case. So cards are stacked against us, I suppose. So that is not even like looking at latent just yet. So now we're looking at the psychometrics that help us to understand the relationship of those hygrothermal the study of the hygrothermal relationship in air, so basically the relationship of moisture and temperature, and now what happens if you put that into air. And you might have noticed, if you follow Joe Stiebrick and John Straub around, lately they have been talking a lot about the water molecule, and understanding relative humidity and how that works, like when you put water and temperature into air, it's a very interesting pattern that develops, and most people are startled when they see the psychometric chart. It's a very complex chart, and I go to that next. But if we talk summer comfort and the impacts of those hygrothermal relationships, well, high humidity obviously is a real problem, makes us feel very uncomfortable, and that problem is compounded in a passive building because there's no airflow. We are super insulated for the winter case, and we're already making compromise there. So we're trying to sweat, but because if the humidity now is high, like remember, like in the winter case, we want like 40 to 60% humidity for a comfort range. Well, I like to pose the question here, is like 50 to 60% relative humidity even comfortable in passive buildings? And I say this because I live in one. And as soon the relative humidity goes up into the 50s, I feel very uncomfortable, and the evaporation from my skin is being interfered with. In addition to that, no ventilation, no air movement, as I mentioned earlier. So we need to understand what is happening here and what influences our comfort, but also how our passive building principles that we're applying for the winter case, how that is possibly kind of stacked up against us in the summer case as well, similarly to insulation. And again, we need to find the right mixture and the right level of all of those to take advantage of them to minimize our mechanical systems, to reduce yet again active cooling, which seems to be becoming more and more the culprit for global warming in a warming world. So the nice thing here, though, is high humidity has less of an effect on the winter comfort, but obviously in the winter it's mostly a condensation risk. But we knew about this already. We've been running our WFI models to prevent condensation in wall assemblies. Now let's look at our options for cooling, and obviously that very much depends on temperature and the relative humidity, and you can see right here the little scale. Evaporative cooling or ventilation, now here the temperature is in form of a dew point. Evaporative cooling or ventilation, i.e. air movement, is a fine option on the low end of relative humidity in hot and dry climates. Mixed and dry climates, relative humidity, once it goes up to 40 to 60, ventilation, air movement, air conditioning, at that point, evaporative cooling is no longer going to cut it. And then as we move into more humid climates with even frequently reaching higher dew points like 70 or even up to 80, we'll definitely have to air condition. So this is the psychometric chart in a much simplified way. This is not the one that you get when you download it from Carrier or from any mechanical engineering site. But this is just to kind of like basically explain the different chart factors here that help you to assess the relationship of moisture, temperature, and then all that in air. As you know, warmer air can hold more moisture, and this is not a linear thing. The colder the air gets, the less humidity it can hold. So this is why you're seeing those curves develop here, because the warmer the air gets, the more air it can actually hold. So the horizontal lines, humidity ratio and dew point. The diagonal lines depict the wet bulb temperature and enthalpy. And then, of course, the curvy lines are the relative humidity, and the vertical lines are our dry bulb temperature. All right, so how can this help us to assess comfort? ASHRAE 55, I mentioned that earlier, depicts a comfort zone. So humans are comfortable within a certain range, a combination of air temperature and humidity, and that is fairly well understood. And from that gray zone right here, then we can assess if we are outside of that comfort zone or not, and then we can pick our appropriate strategy for cooling. I figured it was worth mentioning the relationship of humidity and temperature and air is not always the way we expect it. So, for example, this slide right here depicts the cooling design conditions, and I was very surprised seeing this. I mean, I know in Chicago we are in a fairly humid climate, but I did not know that we were up there as much as we are with Memphis and Miami, and much further away from like Fairbanks or Vancouver, for example. So you can see that the humidity levels up those three cities up high, they have much more challenging climate conditions. And from living in the Smith House, I know that because I experience it. But this is a nice way to actually map it out. So this is yet again how the psychometric chart and those relationships between those different comfort condition criteria or factors can be used to identify a cooling strategy for your summer comfort case. Just quickly, I don't have time to go into this in more detail. But essentially what we are trying to do is we're trying to get us into this little blue zone right there. Now the little blue zone right here, that would be the thermos bottle, no active heating or cooling passive house zone, and that is a very narrow zone. And I can tell you this from my own experience. In my passive house, we try to do as much as we can with natural ventilation and thermal mass to reduce our cooling needs, our active cooling needs. But it is challenging because the dew point many times is very high, and the humidity is super high outside, and there's no point in loading up the building with humidity if you are trying, if you will have to try to sensibly cool it back out, dehumidify the air. So there's a definite limit to natural ventilation. The drop in temperature is so small because also the night temperatures don't drop far enough that it is worth it to bring in all this additional humidity that then poses a challenge to comfort. So just a couple other zones right here to expand the comfort, thermal comfort in summer by various strategies: evaporative cooling, high thermal mass, natural ventilation. It's all pretty theoretical, so let's just go through this. So I like to say that I believe these are right here. These are our set points for passive houses that we've been designing to: 68 in winter and 77 in summer. Again, 68 in winter is likely quite appropriate, especially like you always have the option to put on a sweater, or you can extend that thermal comfort range. There are no drafts, so I think we're probably okay with a 68. But on the upper side, I have come to the conclusion that probably 77 and the relative humidity range is too high because of those psychometrics, the relationship of moisture and temperature in the air. It really does impact your ability to evaporate and to feel comfortable as soon as the relative humidity is above 50, and we will have to reevaluate that. So now, when it comes to systems design, essentially what we're talking about here is reducing our sensible peak loads for the summer case, just like we do in the winter case. But the thing is, we really have very little at our disposal to also reduce the latent loads, the humidity that we would have to take out of the air to feel more comfortable. So essentially, when I'm saying 56 is not acceptable and uncomfortable, I want to get it down to 50 and 77, I need to dehumidify. Why do I need to dehumidify? Because now my envelope is so good that it actually has brought the sensible load down so much, and my peak load is now so small, and my air conditioning system is so tiny that it runs so little that it has no longer the capacity to take out the humidity that I needed to take out. So the conclusion here is the more we reduce our sensible peak loads, we also need to look at dedicated dehumidification to maintain our comfort zone in these buildings. And so this slide right here is actually a graph of what a mechanical system has to provide in the climate, a low load, super low load mechanical system has to provide to maintain comfort in the climate of Urbana, Illinois. That's where my house is constructed. So you can see that the capacities of these systems are very low. On the right-hand side, we go into cooling. There's no more than 2,000 watts. Left side, we go into heating. And then there's also dehumidification. But so what we find is that from practice in Urbana, the low cooling capacity is often challenged by also having to dehumidify. So it is really important to understand what the peak condition for dehumidification is, what the peak condition for cooling is, what the systems selection is that does both of those. Is it a heat pump? Is it a combined system? These systems have to be designed very specifically for this condition in each location, and the mechanical systems designer has to take a good look. What is being done today, just because we don't have such small systems, except what I mentioned earlier, the CERV, which we're kind of experimenting with right now, how much capacity do we need to still stay comfortable? But most designers just put in a mini split, and those are too big. We can't really get big enough systems. I'm sorry, small enough systems for our low loads. And again, then we get the part load problem, sensible to a heat ratio that the system is not really able to do heating and cooling both, because again, when it sensibly cools, it runs too briefly and then transports the humidity back into the space that did come out, some of it anyway, and is not effectively dehumidifying the space. So I know I'm coming up on the hour here, but I think very quickly going through a couple of these examples to conclude is important. So I'm just going to do that. Please hang with me. As I showed during the last part, Phius Plus 2018 is coming up. And what we did under Phius Plus 2018, we came up with even more granular climate-specific guidance for designers for demands as well as for load. And I just quickly wanted to show you here the difference between small building and big building, and how it affects the cooling total and then also the comfort in the building. So as a reminder here, small building in climate zone 5, we have heating demand that dominates. We have still a fairly high cooling demand because again, we have the internal loads and people and activities in the building stacked up against us. So we still need cooling to maintain our comfort zone. But you can see here the heating load is still bigger than the cooling load. And please note that the heating load in North America, most of North America, is almost never 1 watt per square foot, which is the peak load, one size fits all, same kind of strategy there under the PHI standard. In this particular case, it is almost twice as much, and that matters. It matters for sizing the system correctly and being able to maintain the building's comfort zone. So a few words as an example here to the Smith House. This is a cold climate picture, obviously, with a little infrared shot in there. As I said, performs like a champ in the winter, but the summers, in all honesty, are very challenging. And they are because we're refusing to just do what everybody else is doing, to install a 9,000 BTU heat pump. We're trying to really figure out what is the smallest possible active system that we can install. Right now, I say it again, we have a CERV installed to maintain comfort in this building. And to maintain comfort, when I say this, I say it's a combination of strategies of passive, like natural ventilation, but also smart operation of the CERV, shutting down the windows, not loading up the building when we know that humidity is too high outside. So we are really trying to figure out how to make this work. And our next option here, it's still running very warm. That's what we're running up against. If we over-insulate, this building was still designed to the original PHI standards in 2002. So those buildings using the PHI standard have the tendency to be over-insulated and run very warm. So we're now, as a next step, we're going to experiment with fans. Can we increase ventilation and airflow and therefore expand our comfort zone after we have taken steps to control humidity and thermal conditions in relationship to our indoor environment? So another single family example here measured. So that speaks to the internal gains that they impact cooling. The measured data was here in the middle bar. The modeled was on the left, and you can see the modeled predictions were predicting quite a bit more heating in this relatively mild climate in Oregon, also designed to the original PHI standard. That again shows that there's a pretty significant 25 to 30% discrepancy from model to measured because the standards are not precise enough to inform the designer of the middle ground between the heating and cooling condition. In addition to that, if internal gains are not appropriately assessed, and again in PHPP the internal gains assumptions are much too low, you will end up with much more cooling because you need to cool out the internal gains and activities in the space. And that's exactly what you're seeing in the modeled graph. The big blue one is much bigger because there was cooling that was not accounted for. This is initially a climate there shouldn't be any cooling. It's a mild climate. They don't know any cooling. We inadvertently created cooling where if we had balanced the envelope and potential for cooling and assessed the internal gains accurately, we could have optimized this design. That all said, it's still a fantastic building. They do have an active cooling system. They are not overheating. They're not complaining. What I'm trying to say here is like, if we have more granular design data, we can make these buildings even better. All right, so now let's switch to big buildings, 100,000 square feet here. Talked about this last time briefly. Under Phius Plus 2018, now we have more granular targets also for different building typologies. So bigger building, now you can see right here because they're internal load dominated, the energy balance actually flips from being heating dominated. In the same climate, small building heating dominated, big building now is cooling demand dominated. So again, I like to emphasize us solving the cooling problem because it is inherently a problem. The refrigerants that are being used right now in those systems pose a challenge to add to emissions. We have not solved that. We don't have a refrigerant yet that is foolproof and that will not leak, will not add to the problem. So the better we can design and the more we can minimize our cooling demand, the better. Now, on the positive side here, the peak loads really go down in these big buildings. Now, that's a good thing because our small systems now, it even fits into the budget that the PHI says, right? Like 1 watt per square foot, 3.17 kb, 3.17 BTUs per per square foot an hour. So it fits into that budget. Now the problem here, though, what we're not seeing is because those systems are now so small. If you're in a humid climate, we're now compounding the problem of the sensible heat ratio issue. So we're definitely going to need to look into dedicated dehumidification in these bigger buildings because that balances now even more off than in single family conditions. So very quickly, bigger building case studies here. I want to zoom in on the Knickerbocker here for a second because we have monitored data for that one. I'd like to show you the difference here. The dark orange line on the bottom, that is the initial PHI model, old standard. And the blip in the middle there, that is essentially, that shows you, the site electricity that is being used, and that blip on the bottom is what they expect the site energy to increase for cooling. The light dashed line, the kind of salmony color, is the site electricity assumption under the new adjusted Phius Plus model. So quite a bit higher and quite a bit closer to what was actually measured. And then we're very happy with how the new adjusted model aligns with the measured for the cooling case in the summer. But you can see that there's still a pretty significant divergence in the in-between seasons. So again, these buildings are running warmer because in the in-between seasons, we're starting to take on some solar gains and our insulation starts to work against us. We're no longer in the optimal kind of scenario of like losing enough heat for that particular condition. People start to air condition again. And then there's still the riddle for this one, why we're off so much with heating. Could be that solar gain also makes the building run hot in the winter and people open the windows. That's our best guess. We've tried everything else. But the cooling case right here, we seems to have very well under control. In conclusion, so let me say this again, I've stressed this throughout over and over and over again, climate-specific heating demand, cooling demand targets are necessary to determine the right level of insulation to minimize overinvestment and minimize overheating issues. Peak load guidance is crucial to accurately assess, specifically by climate, the hygrothermal comfort. We will not be able to design the right appropriate system if we don't have that guidance as designers. Multifamily buildings have these issues compounded that we just went through. And with all that said, I do not have a crystal clear set of rules for mixed climates, for mixed humid climates, for the designer, because it is quite complex and needs to be analyzed on a case-by-case basis. We would very much like to get there at some point. The tech committee has that on its list of research topics, and there's still a lot of work to be done, including measured data, confirming that we have the right set points for our models to then in the end have good results in how far they actually match up with the buildings in the field. To end on a positive note, with all these kind of like little bit like, okay, we need to get better here in the cooling case. Lisa was just presenting at the New Gravity Conference in Philadelphia. We've continued our collection of monitored data from various projects. This is like single family and multifamily together. The multifamilies are the ones who are a little bit higher because that's where their EUI runs, like right around 20. The single family on average run around more like 14 or so. And then in the middle, the really good news is that if today all new construction was to use passive building standards as building code, this is the site EUI that we would be able to achieve on average measured. We are achieving a 17.7 site EUI kBTUs per square foot in year, and with that a 60% reduction compared to the RECS 2015 typical residential energy use reduction. That's site energy, and sources like between 30 and 50 if you look at different typologies, like from multifamily to single family, and that is significant. If we could make that happen on a widespread basis, we would be well on our way to do our part to stabilize the climate. With that, if you're interested in all this, to discuss this further and to check out where the passive community is at in their solutions and projects implemented, please join us at the 13th Annual North American Passive House Conference in Boston. Great place to be at. Massachusetts is moving very quickly. They have political will. It looks like they will be the next state that will make a move in regards to high performance codes towards passive building. So please join us. Hopefully we'll see you in Boston. And here's your verification code, self-reporting code for the learning CEUs. Thank you very much for your attention. Back to you, Anissa.
Thank you, Kat, for a very informative presentation, and thank you all for sticking around. I know it's just a little bit past the hour. What we're going to try to do is we just have an announcement or two, and then we'll try to answer some of the questions that have come in during the presentation. There have been quite a few questions, so we're going to try our best to at least get through a few of them. So if you'd like to listen to the Q&A, please stick around. But as Kat mentioned, we have our conference coming up. The link is included in the chat box, so please be checking that if you're interested in signing up. In addition, you'll see in a moment a link for our newsletter, so you can get the latest updates on our upcoming webinars and events as well. So please check that out as well. So we're going to move into questions. We're going to do this in order as received. So starting with, what about unzipping our coat when the enthalpy conditions are favorable? Opening windows or operating ventilation in economizer mode would be analogous to unzipping that parka.
Yes. So that would be my first step as well. I would unzip that parka. Um, uh, as a next step to choosing a parka that kind of like is in the middle between of those conditions. Yes, absolutely. So that said, your unzipping only does so much for you. So if you unzip a typical San Francisco parka on July 21st on Times Square, you'll feel a lot better than unzipping a Fairbanks, Alaska parka. So there's still something to be gained from finding that healthy middle ground insulation level and optimizing your losses. That's your first passive step, optimize your losses. And that is, by the way, also a reason why we have gone to allow double pane windows in multifamily construction, because it's important for the cooling case. In the cooling case, there is actually an improvement of the annual demand by increasing those diurnal losses through the windows. The total cooling is less over the year with those windows. So, of course, you can only relax the performance of those windows so far that they don't pose a comfort or condensation issue in the winter. Of course, that is your stopper. That you cannot relax them any further. So, but yes, the question that was asked, these are all great strategies. Economizer, if the conditions are right, if the humidity is not too high, that's a very fair strategy. I forgot to mention, actually, under 2018, we completely took out natural ventilation. And the reason for that was that we saw a lot of kind of like gaming the system. People were claiming a lot of natural ventilation, while it wasn't always clear that that was actually going to happen, because it was kind of like somewhat relying on the occupant. But it is also the case in multifamily projects, we often found that there's a lock on the window. So people really can only open it 4 inches. For one, and then there were studies done, do people actually do this? And many studies said people were not opening windows that made any sense. So that we took that ventilation piece out because we can't certify occupants. We cannot rely on that, and we cannot rely on people to do the right thing depending on the exterior conditions. If they do, it's a plus. That's great. Next question.
Next question, in terms of comfort zones and multiple people in families, does this mean that there should be some sort of individual testing or surveying of clients to try and develop a happy medium strategy in terms of comfort levels for a home?
Yes, yes. I would strongly encourage that. So I was trying to hint at that with my story about Mike and myself having very different metabolisms. It is really notable because when you're operating in a comfort zone that pushes up against some critical threshold so closely, one person will very quickly feel super hot and the other person is still fine, right? So either the designer needs to know the range of people in a way for best results who live in the building, or just take the approach like, I'm going to design the comfort zone a little bit bigger and then everybody's going to be happy. So that's obviously good as well. But I think it would really inform all of us if we could have a survey of sorts, how people feel about the comfort ranges in the different passive houses and how successful they think we as a community have been to get them into the zone, if you will.
All right, next question. If you are reducing the summer set point temperature from 77 degrees Fahrenheit, will the cooling demand thresholds be increased?
Well, we haven't done that yet, but that would be a logical conclusion, right? So when we do our assessments, we get monitored data back from projects, and there's a discrepancy. Of course, first thing, an easy thing that you can check between measured data and model data is you set your model to like what if they ran, and maybe even you have data from the VRF manufacturer, what the average actual set point was, and then you can fix that in your model and you can see what happens. And of course, in many cases that then goes above the criterion. So yes, so if we decided to do that, we would have to adjust so that it is actually doable. But I think we're also not doing ourselves a favor if we just have aspirational numbers in our model, which then people don't use. So that leads to basically us predicting um, uh, energy consumption uh, on a whole that then has an equivalent of carbon emissions that then the code official will use to check if they met their targets or not. So that there are real world implications if we are designing buildings with targets that then in reality are not being used and they exceed our predictions. We really do ourselves a favor if we accurately account for what people will do and then deal with what the result is and then accurately show that in our carbon balance, because it's a non-negotiable. We have to meet our carbon reduction target, otherwise bad things are going to happen, right? So accuracy is really important.
All right. We still have a few more questions, but I think maybe we'll have time for about one more. Does that sound about right, Kat?
That sounds fine.
Okay. So our last question, could ERV preconditioning help this problem by directly addressing the air introduced into the building?
Yes. And I couldn't go into this into detail, like we just have an hour, right? Yes. So if you are in a humid climate, and again, it also depends on building typology. If you're in a humid climate, um, an ERV will help to reject some of that humidity before bringing the ventilation air into the building. And that ventilation air in humid climates is a big chunk of our conditioning needs, the removal of latent air, because that affects our comfort zone. So the answer to that one definitely is yes, but it gets complicated quick when you look at all the different options. For example, in multifamily buildings, the ERV, um, and during some time of the year, you might be better off with an HRV because the humidity loads in the building might be higher, and the ERV will, if the humidity loads in the building are higher, will retain the humidity on the side of the higher concentration, but you might have to get rid of some humidity. Your latent removal conditioning need of the air might be bigger than the sensible, and you definitely will want to maintain your relative humidity within the 40 to 60 just for like healthy indoor air and mold avoidance, right? So it needs to be looked at by a mechanical engineer because we're improving the envelope so much. I've said this a long time ago. This is not to get rid of the mechanical engineers to minimize the system. The complexities of the system are still the same, if not greater, because we have less tolerance in the design and in the system.
Well, that's about time for us on our end. We appreciate all of you sticking around for the Q&A portion. Thank you again, Kat, for this very, very insightful presentation. As Katrine had mentioned, there will be a recording available, and you will get notification of that within a week. In addition, please take a look at this screen and record this verification number so you can self-report for any CEUs you would like to obtain. We look forward to seeing you at another webinar coming up. Stay tuned for a September webinar, early September. As mentioned before, there's a link to signing up for our newsletter, as also signing up for a Phius membership if you liked what you heard today and you wanted to get some membership perks. So thank you all again, and we hope you enjoy the rest of your day. Thank you, Katrine.
Thank you.